example 31 in the notes there. I see that we've got function f, and it's got derivatives of all orders for all real numbers. Third degree Taylor polynomial is given up at the top, t of x 7 minus 9x squared, minus 9 times quantity x minus 2 squared, minus 3 times the quantity x minus 2 cubed, all right? And there's a part A and a part B, but I actually want to skip down to part C, just the first part of it. The first part says, use t of x to find an approximation for f of 0, all right? So to find f of 0's approximation, we plug 0 into t. When we plug 0 into t, we have 0 minus 2 and 0 minus 2 in both sets of parentheses, which is obviously negative 2. So we end up having 7 minus 9 times negative 2 squared, minus 3 times negative 2 cubed. Negative 2 squared would be 4. 9 times 4 is 36, so we're subtracting 36. Negative 2 cubed is negative 8, times negative 3 is positive 24. 7 minus 36, negative 29, plus 24 gives us negative 5. All right. So you have to do that in part C. Now, let me read part D to you while you're looking at it as well. The fourth derivative of f satisfies the inequality that the fourth derivative is absolute value is always less than or equal to 6. That's what we have right here, right? And that's true for all the x's between 0 and 2, right? Use the Lagrange error bound to find, on that approximation that we just found, to explain why f of 0 must be negative. Okay, so as I mentioned in the previous video, what they're doing here is what they commonly do in the exam, where they tell you the maximum value of the next derivative, all right? They're not expecting you to find it or necessarily understand what the maximum value could be based off of the function. They're quite often interested in just giving you that maximum value and seeing if you can go ahead with the Lagrange error bound formula. Okay, so let's do that. Now we know that the formula, all right, is going to be the maximum value of the function of the next derivative over that n plus 1 factorial times the absolute value of x minus a to the n plus 1 power. All right, and our error is going to be less than or equal to that. Okay, so just let's punch in our numbers. All right, we're given right here the maximum value of the fourth derivative is 6. So 6 is going to head into our numerator. Okay, again, we have a cube here, so 3 plus 1 gives us this 4, and it also means that we're doing 3 plus 1 here and here. So we have over 4 factorial, and then in our absolute value, we're going to raise that to the 4th power. Right. What are the x and the a? Well, the center of the series is at 2, so we're subtracting 2, and we're interested in 0. Okay, when x is 0. Notice the absolute value, so even if you swap those, no big deal, you're going to end up with 2 when all is said and done. So we have 2 to the 4th from this part right here, so that's equal to 6 times 2 to the 4th over 4 factorial. All right, well, what's 2 to the 4th? All right, 2 times 2 times 2 times 2, that's 16. So we have 16, so 6 times 16 over 4 times 3 times 2 times 1, which is 24. All right. And, well, we can do a little simplifying here if you want, or 6 times 16 is 96. 96 divided by 24 is going to be 4. So the error is less than or equal to this formula, which happens to be 4. At most, our approximation is off by 4 units. That's what we just found. At most, our error is 4. Well, what did we come up with for an approximation? Negative 5. So the most that we could be off by is 4 units. If we were 4 units off, that means the answer could be, the actual value of f of 0 could be up to negative 9 if we travel in one direction, or over to negative 1 if we travel in the other direction. There's no way for us to get to a positive value for f, because if we have negative 5 plus 4, that's equal to negative 1, which is still less than 0. So we could draw the conclusion that f of 0 is definitely going to be negative. It's somewhere between the value of negative 1 and negative 9. We don't know where it is exactly. It's somewhere in between there, but we definitely know it's between negative 1 and 9. The error bound caps the range of how far off our approximation actually happens to be. That's the idea behind the Lagrange.